In a previous video, we talked about geodesics for particles that have non-zero mass. Today, I want to investigate basically the same thing for particles whose mass is zero. Or, what's up, photons? There is no frame of reference in which a photon is at rest, so a photon doesn't have a four velocity as such. On the other hand, I can calculate the derivative of its position with respect to some parameter that describes the path of the photon and get a tangent vector. So this u is not the usual four velocity, but it is a tangent vector. When I say something moves along a geodesic, I mean that its tangent vector never changes direction. Since u dot u will be zero for photons, I can write that as this, where lambda is some parameter that describes the motion of the photon. I can't use proper time, of course. The usual manipulations lead to the usual formula. If I can find formulas like this that describe the motion of the photon, I'll know the geodesics. Of course, for photons, as I said, there's a little bit more to it than that. U dot U is 0, not -1. The same symmetries apply to the metric as in the massive case, though. U sub 0 and U sub 2 must be constants. If R is very large, then dt d lambda is equal to E. E expresses the relationship between parameter lambda and the coordinate time. U sub 2 being 0, and assuming that the motion we're interested in happens in the hypersurface phi equal pi over 2, we are led to the same formula we had before, except instead of proper time, we have this unknown parameter, lambda. In what follows, almost every calculation that we do is identical to the one we did before, so I'm just going to show you the calculations without talking my way through it all. As before, using the constants of the motion, E and H, we can reduce this down into this equation. Let R be 1 over U. By the chain rule, dr d lambda is -1 over u squared du d lambda, but du d lambda is du d theta d lambda because of the chain rule. Because of the conserved quantities, though, d theta d lambda is h over r squared, which is h times u squared. So dr d lambda ends up being the negative of h times du d theta. In an upcoming video, we will look at two of the three classical tests of general relativity. One of them is the orbit of Mercury, and the other is the bending of starlight by the gravitational field of the Sun. Until then, I hope everybody has a good day, and I'll talk to you again soon.